John Butler will be speaking to us about the graphics program interface. John joined Microsoft in 1982 and has been working on the GPI ever since. But John's interests in graphics go beyond Microsoft. He's been a very active figure in the ANSI Graphics Languages Committee, and he founded the ANSI task group working on windowing software standards. Because of the importance of graphics concepts in the Presentation Manager, John will be starting with an overview of graphics and will gradually work his way down to a more detailed look at the important graphics services provided by OS2. John will be taking a close look at coordinate systems and transforms, text and graphics issues, and the GPI function calls in Presentation Manager.
In this talk, we're going to be taking a look at how Microsoft is providing device-independent graphics for OS2. First thing for us all to agree on is what's the name of the functionality that we have provided to do graphics. And the name that we have given to our graphics services for OS2 is the Graphics Programming Interface. That's GPI. This is an extension and an evolution from the previous version of graphics that we had for Microsoft Windows, which was called GDI, Graphics Device Interface. And we'll take some further looks at what it is that makes that difference. During this talk, what we're going to do is take a certain amount of time to look at the general concepts embodied in graphics. Where have they come from historically? Where would you go to study the kinds of things that we brought to the systems level in the GPI interface? And then we'll turn to a look at the function groups in a little bit more detail. We'll begin each group discussion with a look at the concepts that the group embodies, and then we'll take a look at a few of the important functions in each group. With that as the background to what we'll be doing in the next few hours, let's begin then with an overview of the concepts embodied in Microsoft's graphics programming interface for OS2. The first thing to note is that the GPI brings to the systems level API all the benefits of both a high-level graphic language and a super device interface. Now, the reason for that is really fairly simple. That is that the two pieces of the GPI provide different kinds of facilities. The high-level graphics language has as its purpose offloading the work of remembering how to repair a graphic picture from the application itself into the system. It allows the application to store in its internal data structures a representation of the data which is optimal for the abstract operators on that data that the application provides. For example, editing the contents of a spreadsheet or editing a text file, if you will, for a word processor. The device interface has a very different purpose. What it does is it decouples the system layer from the actual control of individual devices. And in that sense, the device interface then is really much more of interest to the system software layer itself. Now, we'll see how in order to make all that work, applications have to be able to find out about the actual device they're controlling in order to use it optimally. But the two parts of the GPI, that is the high-level graphical language, which offloads the requirement to store data in a fashion which is convenient for reproducing the picture that an application wishes to draw to a client, and the device interface, which decouples the nature of the device being looked at from the system software layer, are the two halves of what GPI is. Let me here note that it is the high-level graphics language which is really the additional component over and above the Microsoft Windows GDI. In a little bit more detail, the high-level graphical language has as its purpose the storing of picture elements so that they can be replayed on screen for the application's use or at the viewer's command. It allows the construction of a picture out of hierarchical elements where each picture element is embodied in a segment about which we'll talk at some length later. And the segments are themselves involved in the construction of an entire picture. Because of this storage and the possibilities of reusing components of a picture over and over again, there are replacement and editing functions provided for various parts of that picture, and we'll take a look at those editing functions. Finally, in order that you, the application author, can figure out what part of a picture has drawn the attention of a user on the screen, we provide functions which can be used to correlate or do what's called hit detection. That is, to correlate the area of interest a user has in a picture with your understanding of the actual picture elements involved. And we'll take a look at that in somewhat greater detail. That is the traditional graphics concept of picking or hit detection, which we have here called correlation. And finally, in the future, the high-level graphics language, which is embodied in the GPI, will allow the system to do automatic picture repair, so that if the user changes the size of a window or deletes a dialog box which is popped up on top of a window, the picture repair facility will allow the system to automatically redraw the picture from its data description for that picture stored in its own system memory. So those are the purposes of the high-level graphics language. A device interface has as its purpose letting each device do exactly what it can do. That is, to perform all of the required functionality which is within the capability of a device. Additionally, it has as its responsibility making all devices look the same. To the extent that you want to draw a circle on an attached device, it's important that you should be able to draw a circle on any device, regardless of whether the appearance of the circle is very smooth because the device is high resolution, or whether the appearance of the circle is very blocky because the device is of fairly low resolution. And finally, in order to allow the application programmer to actually understand and to use exactly the capabilities of a device when it's of interest, we want to provide information about the specifics of a device, so that if you want to find out what's the color of the pen in slot 2 on a plotter, or what is in fact the horizontal resolution in dots per inch and that sort of thing, the device interface provides you with that information as well. I mentioned that we want to look at the historical basis of the pieces of GPI, and I think it's important to do so, partly because until you have the specification for the GPI, it's important that you should know where you should go to read if you want to learn and get a head start on things. And first of all, the high-level graphics language came from a series of sources. One is mainframe. In the world of mainframes, the Graphical Data Display Manager, the GDDM instruction set, is a very good one and an interesting one to look at. From the world of terminals or workstations, the 3270 Graphics Control Program, the GCP for the 3270, is also an ancestor of many of the extensions that we've added in moving the GDI interface to the full GPI interface. Finally, in terms of printed standards, you might want to take a look at the ANS and ISO, the International and American National Standard GKS, the graphical kernel system. That document is filled with good background in some of the areas of functionality which are provided in a slightly different functional interface form with the GPI. The draft proposed FIGS, Programmer's Hierarchical Interactive Graphics Standard, is another place that you might look to learn about some of the aspects of the high-level graphics language which is embodied in the GPI. The device interface has a slightly different history. From the world of microcomputers, we get a lot of support and a lot of commonality with the Microsoft Windows GDI, Graphics Device Interface. From the world of terminals and workstations, there's some heritage related to the Smalltalk language and the way it performs some operations. And from the world of printed standards, the draft proposed Computer Graphics Interface, the CGI so-called, is another excellent textbook on the concepts which we have embodied in the device interface. We were involved in the early definition of the chapters on raster primitives and the use of coordinate systems and 16-bit integers in particular in the early drafts of the evolving CGI. Let's turn now to an illustration, a graphical illustration of what exactly it is that we have defined as part of the GPI. There are really two things going on. One is, for applications, we provide a thing that I have called the high-level graphics language. This is the complete application program interface, API, for graphics, and is available to all applications running within the presentation manager of OS2. For purposes of decoupling the system from devices, there is another interface, the device interface. As it happens, a good deal of the device interface capabilities are reflected up through the high-level graphics language. That is, there are calls defined in the high-level graphics language which get at many of the capabilities embodied within the device interface and in the underlying device. But what we have done then is to really define two languages simultaneously. Okay. That's a discussion then, if you will, of the history and the content and the nature of what's in the GPI. What I want to do now is to take a look at what is it that makes GPI different. Why is it that GPI is not identically the same as any of the standards or the evolving standards that we've named just now? And there are two basic reasons that the GPI differs from those other standards. One is that it is the first instruction set widely available which combines languages for control of both raster devices and vector devices. And we'll turn to a little bit more detail about what I mean by that in a moment. The other thing that makes the GPI different from the others is the extent to which it embodies techniques for doing device sharing. Device sharing for presentation devices, hard copy devices, means using them serially, and is largely solved by spooling output to one printer or plotter until all of the output for a particular application's use of the device is complete. When it comes to sharing interactively, a device which is used, such as the display, for interacting with a human being at the console, will find that a very different mechanism needs to be evolved. This is, if you will, simultaneous or at least concurrent use of the same set of pixels on an interactive device. And the GPI solves the problem of doing that with a number of new techniques. Let's take a look first at what's meant by the difference between raster and vector. These phrases capture the difference, which is as follows. In the drawing on your left, what you'll see is a bunch of blobs at locations, and this is what I like to call the point sample intensity. That is, you take samples at according to some grid, and what you're left with is an array of numbers, if you will, and that's what's called a raster. A raster, then, is this notion of an array of numbers which may correlate to colors or to intensities or perhaps to some other value of interest. On the right-hand side, I've illustrated a pi wedge in 3 dimensions, and this is intended to capture the notion of a vector construct. A vector construct is one which is defined in abstract mathematical, geometrical type terms. Now you notice I've used these terms a little bit differently than they are commonly used, where we think in terms of raster devices and vector devices. What I want to capture here is the nature of the underlying principles in the raster and the vector worlds, because both of these worlds are very important. I'm fond of saying that my human retina is a point sample intensity device. It captures the amount of color at locations, and it creates an array which is transmitted back to my occipital cortex and brought forward into higher center areas. And ultimately, what I develop from that raster image is a holographic tank image which is filled with geometrical objects, including things like a television camera straight in front of me. And it's that difference that we have captured in our instruction set. Because we believe so deeply that the instruction set has got to capture both of these kinds of elements, we provide functions in our GPI's API for dealing both with raster functions and with a vector. For purposes of dealing with raster type images, we provide a rich set of combinations. That is, you can specify to us how you want the numbers at locations to be combined if you're taking, say, one array and placing it onto another, and we'll take a good look at that later on. We provide some facilities for automatically stretching and reshaping an image. Clearly, an array has some implied or designated size that it may take, and if you take an array from one area where there's a certain resolution per inch horizontally and vertically and put it onto another area, you may need that support in stretching. We already provided that in Microsoft's GDI, and we've extended that notion in the GPI. The other thing, which is much richer than we've done in the past, is the concept of automatically converting colors. If, for example, the array of numbers on input are all from 0 to 7, that is meaning one of 8 different colors, we can allow you to have fine control over the mapping of each of those colors onto a new device. In the area of vector primitives, we provide rectangles and polygons and circles, just as have the existing standards. We've gone somewhat further than that in the provision of what we call figures in areas. Figures in areas are complex boundaries which may be made up of portions of lines or portions of circles, and ultimately are really what polygons are in other settings. The intent of the figure area primitive is to capture the fact that portions of the boundary may in fact not be straight lines, but might be curves. For those primitives, we provide coordinate transforms, border and interior controls, where the interior may be hatch styles or bitmaps, type images, and so forth. And in this, our system is just like the others, with the additional stretch that it includes concepts involved with the figure and area type primitives. Now, that's one of the things then that we do with the GPI, is that we provide access to both raster and vector functionality. The other thing that we do is to deeply understand and promote the use of devices in a shared fashion. We do this in two ways. One is with the spooling for presentation or hard copy style devices. This is printer plotter spooling, and involves simply serializing the use of these devices by different applications. I will say no more about that. The process of spooling is well understood and is not really of any further interest to us here. But display allocation is worth some more attention, in particular because we wish to allow multiple applications to all transparently own or think that they own an extent of an interactive display screen. So let's take a look at the problem. The problem that we need to solve is that we have multiple concurrents, all of whom are using a single interactive display. The solution to using those devices is what we call the presentation space. The presentation space is a generalization off of the device context of Microsoft GDI, and is now the key to using devices with the GPI. The two constructs, the device context and the presentation space, allow one to think as an application developer, much as the application writer thought when they drew the picture you see in the bottom of the screen here. That is, there's an image which needs to be drawn for the client to use, to look at, to scale, to redraw, and so forth. And as it happens, in the upper left-hand corner of the screen, you can see that there are currently a couple of other windows up on screen. Now, the human being is using the system, has put those windows there. They take, if you will, some precedence over the picture that the application is trying to draw of an airplane. And in point of fact, it's the human which is in control. And it is absolutely transparent to the application. If it were to try to renew its picture at this time, it is absolutely transparent that the picture space it's drawing into is illustrated in the upper right. That is, it's not a rectangle. It has these chunks taken out of it. It is the responsibility of the presentation space and the associated display device context to make that kind of clipping. It is not the application's responsibility beyond obtaining a valid presentation space for use with its drawing on the screen. Now, in a little bit more detail, the two constructs, the presentation space and the device context, are each responsible for storing some of the state of the graphical system. In particular, the presentation space handles the storage of hierarchical picture elements, which we call segments. Notice this is a concept to which I will recur. But when you think about code segments in OS2, a code segment is an extent of machine instructions which will be performed by the underlying CPU. In graphical terms, a segment is a collection of graphical primitives in a language which is to be understood by the graphical engine that will ultimately consume those segments and reproduce an image on the basis of them. So there is a great deal of correspondence between the use of the term segment in OS2 to mean code segment and the use of the same term segment to mean a graphical picture element. The presentation space also handles the definition of symbol sets and fonts. You'll see that in the GPI, applications can do what I call assert font. That is, they can say, I've got all the data I need for you to draw images of characters on a screen. Here's the font. Use it. You can define your own line types for use in the system. The default attribute settings are all held within the presentation space, as is a logical color table with which you can control automatic color conversion. The coordinate transforms are held within the presentation space. And finally, there's a notion of drawing control, which is part of that space. The presentation space, then, handles all that part of the state. Now, in fact, there are two kinds of presentation space. In particular, that's a lot of information to be stored on a routine basis by every application being used in the system. It happens that we therefore want to provide two forms of presentation space. One of them is what we call the normal space, which includes all that state and can be involved or used with any device context over time by association, as we'll look at. And the other is the concept of micro PS, where the micro PS is usable with exactly one DC and typically used with the interactive screen. The DC for the micro PS is built in at the time the presentation space is created and is actually created with a different function than the usual PS. The purposes of the micro PS is to allow applications to use devices much more directly than would be possible if they were using the PS. Looked at graphically, what I mean to illustrate is that on the left, we look at the full presentation space, which has a lot of area that it covers around the device context. The micro PS is much more conformant in size to the actual device context, as illustrated on the right in the picture. Now, the device context itself has as its responsibility the handling of device access, that is, acquiring control or ownership of the device and turning it on and off and initializing it and so forth. It handles communication with that device, however that may be, through whatever channel. It performs instantaneous state. That is, typically the only state the device remembers is that it's currently drawing lines which are wide and dotted. That's about all it knows. It doesn't know that there are 15 clients out there, some of which hold red wide lines and others of which hold narrow dotted lines and so forth. The device context handles all the clipping to the screen boundaries that we saw, which may be irregular. And it provides to the application program any requested information about the actual characteristics of the underlying device. In review, then, through this part of the talk, what we've looked at is the fact that the GPI embodies both a high-level graphical language, allowing applications to offload some of the work of building a picture in a fashion which is conformant with optimal drawing on screen, and the device-independent interface, which is another aspect of the GPI's API for applications. We've seen that the GPI embodies instructions for handling both raster type elements, those which are point sample intensity type or area or array of samples, elements, and functions for handling vector or the geometrical, mathematically defined sorts of graphical pictures. Finally, we took a look at the mechanism for sharing the interactive device. Now, notice that one needs to obtain a presentation space in a device context, even to share a serial presentation style device. But what we've taken a deeper look at is the way in which the presentation space and the device context are used to share the interactive device, the system display. In the next portion of this talk, what we'll turn to is a look at each of the function groups embodied within the GPI. The intention here is to review again the concepts for each of the groups of functions which are provided in the GPI, and then go into just a little detail about what those functions are. In fact, by the time we're through with this talk, you will have seen pretty much every function that there is in the GPI. I will try not to belabor some of them. There are a lot of them, many of which have very abstruse meanings that are very difficult to capture in the short time we have available. But I want you to have an overview at least. At this point, I should say that anything that's important in this talk you will have heard at least 5 times by the time we're done. If there are unfamiliar concepts that are important, you will discover that you've heard about them in 3 or 4 different contexts by the time we're through. The unimportant things you'll probably hear only 2 or 3 times, and the intention again here is to give you, if you will, a jump start on understanding these additional complex constructs. The function groups that we're going to take a look at in the remainder of this talk include those which are responsible for the allocation and the creation and the use of contexts and spaces. We'll take a look at the graphical segments and the way that they are handled and controlled. We'll look at the transformations from one coordinate system into another coordinate system, take a look at the clip shapes which you can create and manipulate in order to control not just the way the system is going to share the interactive device, but also the way in which you may protect part of an image which you have previously created. And then we'll turn to the actual drawing elements themselves, markers and lines, arcs, which are our curves, fillets and splines, which are new, polyconics, areas and patterns, images and bitmaps, all of which are ways to fill up areas bounded by strokes and lines. And then we'll take a look at the way in which the GPI provides support for text, for things we call regions, which are ways of doing clipping down at the deepest device level. And finally, once you've mastered all of that, you may actually want to save one of these things for later reuse, and you do that in a metafile. Turning then to a discussion of the presentation space and device context, I want to reiterate some of the important concepts embodied in those 2 constructs. First of all, that the presentation space and device context are both involved with the preservation of state over time. That allows you, the application programmer, to allocate a presentation space, to set it up in a way that you want to use it, and then to reuse it over and over again every time that you come back to redraw your image or to cause it to be redrawn. In particular, what you need to do, as illustrated on the left, is to create DCs, device contexts, for whatever devices it is that you're going to be using. You then also create a presentation space. Through an association process, a particular presentation space is bound to one and one only device context at any particular time. On the right, what I've illustrated is the fact that a particular presentation space may be bound to different device contexts over time and used, therefore, to create actual images perceptible by humans, either on presentation devices or on the interactive device. The functions available for you to use presentation spaces include those of creating a presentation space, destroying it. If you want to hand it off to a friend or a bunch of subroutines and you don't know what changes they're going to make to the coordinates or the transforms or anything like that, you can save the state of it and restore that state later on. When you want to make use of a device context which you have obtained through other functions, you can associate a device context with a presentation space. And finally, when you're actually doing drawing, which may be done asynchronously, as we'll see in a bit, you can synchronize that drawing with your activities, the rest of the activities in your message processing loop using the GPI synchronize function. The page is, if you will, the default coordinate system in which the presentation space draws and is settable by various functions and also inquirable. Those then are the set of functions which relate to the creation and the association of presentation spaces with device contexts. The functions available for creating device contexts are very, very similar to those embodied in the Microsoft GDI. The next group of functions that I want to take a look at is those related to segments. And again, I want to emphasize that by segment here, I do not mean an extent of machine instructions for the CPU, but rather an extent of graphics instructions for the graphics imaging engine. It may be that there is a device driver, for example, which ultimately uses the system's CPU to create images, but it is that graphics driver that understands the elements of a segment. A segment, then, is a collection of graphical calls which are stored for later reuse, and these are the picture elements as defined within a segment. The system in GPI is designed so that segments may call other segments hierarchically, and we'll take a look at that when we take a look at the way in which segments actually draw and create images. And finally, the set of current segments, the set of segments which are available and will actually be drawn from, forms what we call the picture chain, and that picture chain is the subject of drawing. Segments in the picture store of a presentation space may be created or deleted. They may be transformed geometrically. They can be edited, and they can be reordered in the chain. Notice that in a presentation device like a raster device for a display, typically the last time a pixel is painted is the color that it takes on. By reordering the order in which segments are drawn, you can change the ownership, if you will, of a pixel from one segment to another. GPI segments have a number of attributes which are settable. Segments may be detectable, that is in the process of correlation, where you're trying to discover whether a user is looking at, say, the left front tire or the right rear tire on a drawing of an automobile on the screen. You can decide whether either of those segments is detectable. Segments may be visible or not. They may be in the chain or not in the chain. They may be highlighted for you to interact with a human being to say, is this the segment you want? Highlight that segment system. They can be made dynamic, in which case they can be picked up and dragged around at will. And finally, if segments are built hierarchically, any calls to other segments from within a segment can propagate the attributes of detectability, highlighting, or visibility. The function set, which is provided in the GPI for handling segments, is very rich, and let's take just a very brief look at it now. It includes the ability to open a segment and close a segment. Segments can be reopened for later use with the open call so that you can do editing on them. When you're through the segment, you can delete one or you can delete a group of them. And if you've forgotten what their names are, where names are all integers, you can get back the set of names currently available in a presentation space simply by asking. In order to control drawing and ordering of the way in which segments are drawn, you can set a segment's priority or find out what its priority is. The order parameter can be one of in front or behind of all or one. Therefore, you can set a priority so that a segment occurs at the last end of all of them, or you can set a segment so that it occurs just in front of a particular segment. In this fashion, you can quickly shuffle the ordering of segments in the drawing chain and change the appearance of the image to the human being. Each segment has a set of initial attributes it takes on, that is visibility, detectability, highlighting, and so forth, and you can both set the initial segment attributes and inquire what those initial attributes are. Dynamically, after a segment has been created, of course, you may also, individually or as a group, change any of the attributes. Those are the functions that you use to create segments. Well, that's fine. You got a bunch of segments which are a collection of picture elements sitting out there. But I also alluded to the fact that if you have segments out there whose contents has been invalidated by actions that the user has initiated with your application, you need to be able to perform editing functions on those segments. The concepts here, then, are embodied around the fact that segments contain elements where each element generally corresponds to a call to a graphics instruction at the time the segment was open. These elements may be edited one at a time, either by deletion or insertion. They may be referenced by name or even by number, where by name you can actually insert an element into a segment that has a name, and you can refer later on to that label as an element and move your pointer in the segment, if you will, in order to enhance your control of the editing process on that segment. Editing may be, as I mentioned, either insertion or replacement type mode. Again, there are a number of functions related to the editing of segments. First of all, you have to be able to set the mode. Are you going to do replace or are you going to do insertion? And once you set it, you need to be able to find out what it was so you can change it again if you forgot. The element pointer functions are all involved with moving the element pointer in the currently open segment to a location that you previously determined. You can move it to a number. You can offset it from its current position by some increment. You can set it to a label if you remember the name of the label. And finally, you can figure out where it is simply by inquiring. All of those functions allow you to move around the pointer. All editing actually takes place at the element pointer. You can delete the element right under the pointer by simply calling for a deletion. Or you can delete a bunch of them. And there are two ways to delete a bunch of them. One is that you can inclusively delete all the elements in a particular range, but say the first and last elements were actually labels that you wanted to leave because you wanted to define them later on so you could insert more new contents. You also have an exclusive delete for which you could name two labels and delete the extent of graphics instructions between those labels. You can find out you can place an element in there by beginning an element and adding data to it and then ending it. It's important that that element should be understandable by the system. There are no user-defined elements per se, but you can inquire their actual structure using the query element instruction after you found out what its type is. These functions are related to the storage of actually binary data in the segment itself. So there are lots of ways that you can change a graphical segment once you have created it. Well, that's fine, but we haven't made it appear on screen yet. Making segments and images appear on screen or on a presentation hard copy device is a function of the drawing functionality embodied within the GPI. Drawing concepts involved in the GPI include, first of all, those related to creation and storing of a picture. The segment open type call has to do with the creation of a stored image, and the drawing functions have to do with the actual drawing on screen or a presentation device of the set of calls embodied in the segments currently in the chain. The drawing concepts then allow you to create a stored picture without drawing it anywhere, or to draw and store the picture at the same time, or to simply draw a stored picture. Finally, the drawing concepts also allow you to do what we call hit detection. That is, if you want to correlate the area of interest a user has expressed, say the user has roved the mouse around and you've got the mouse cursor lying over some portion of a picture that you've generated. What you now wish to find out is, where in the heck, which segments? Is that the left front tire, the left rear tire, or is it, some other part of the car body? Which elements in which segments and which segments called from which other segments have been selected by the user for use? That's called hit detection. Very much as in a menu, what you care about at the system level, what the system cares about, is discovering which menu item has been selected so that it can return an identifier of that menu item to the application. The concepts embodied then in picture storage are as illustrated in this diagram. On the left, what you can see is what I've called the picture chain, and I've drawn a box around that just simply for completeness sake. The picture chain begins with, is really segment 0, and it includes a bunch of instructions for setting default attributes perhaps and so forth, and then moves on to a call to segment 1. Comes back, and after a bit, calls segment 2. After calling segment 2, the picture element creation process returns to the chain, and there may be more instructions right there in the chain in this segment, and finally another call is issued to segment 1. That then embodies the length, if you will, of the picture. Now there are a couple of things I've intended to capture here. One is that a graphical segment may be referred to more than once. That wouldn't make any sense unless you could put it on different places in the picture. And in fact, there are functions that we'll look at later exactly related to moving the appearance of segment 1 in both of those calls. Number 2, the concept I want to illustrate is the fact that segment 3 is not referred to at all. It is not part of the current picture. It has been, if you will, edited out because there are no references to it from either the segment, the drawing chain itself, or from any segment called within the drawing chain. And there are therefore two important concepts embodied in this diagram. One is that on the left we have the notion of picture chain. The chain refers to all those segments which make up the current picture. It is traversed starting at the top and ending at the bottom. Drawing control specifies what parts of the chain are to be redrawn and how they're to be redrawn and so forth. And the other important concept embodied in this slide is the fact that some segments may not be part of any particular chain, although they have been defined, presumably for later use, as part of a picture. The actual functions in the GPI to control the use of the segment store to refresh or create images has to do, first of all, with drawing control. The functions for setting and inquiring drawing control are embodied in this fairly complicated set of parameters, the control and the value parameter, which specify, for example, whether you want to say, let's run through this list of segments and figure out what the boundaries are in the coordinate system that I'm using. Maybe you forgot or you don't know. You can perform hit list creation. You can say, okay, here's a value. I know where this value lies in the coordinate system, but I don't know what elements in my picture come near that value. And that's the hit list creation concept. You can say, draw the chain and tell me what elements in what segments, called from what other segments, actually are in that arena or in that area, coordinate-wise. You can decide whether drawing should be done synchronously, start at the top, go to the finish, and then tell me when you're done, or whether they should be done asynchronously. Clearly, in the setting of a complex graphical coprocessor, what you may want to do is to kick the coprocessor and say, okay, go draw this thing, then return to me. I have other business that I want to accomplish while you're finishing the drawing. You can decide whether the drawing should be done visibly or invisibly. It may be well, I'm not even going to try to motivate for you why it is. There are a number of these concepts that are not immediately apparent and take a little bit too long to describe. But suffice it to say that invisibility is sometimes useful if all you're doing is hit detection. You may want to control messaging. If you're doing asynchronous drawing, you may want to be told when the drawing is done, and that's what message control is all about. And finally, you may want to say, well, okay, let's erase this thing first. In addition to the drawing control, which you set and is static within a presentation space, there's also the concept of drawing mode. The drawing mode specifies whether the elements and the function calls that you make are to be used to create a stored picture only, to draw a picture only, or whether what you want to do is to draw and store a picture at the same time. And that's embodied in the functions of drawing control. Finally, when you set everything up, you've got pictures and segments created, and the chain is all ordered, and everything's in the right priority. What you need to be able to is actually do some drawing. When you say draw chain, the chain is begun according to the currently set drawing control attributes in the drawing mode, and the whole thing is drawn from start to finish, or according to where you said it should be drawn. If you only want to refresh part of the picture, and you know which part, you can say, let's redraw this particular segment. Or you can do an inclusive draw from segment 1 to segment 3. And finally, in the event that you've been doing asynchronous drawing, what you may want to do is to say, okay, let's stop the drawing. I just got a message. User hit Control-C or something, and I'm going away. Let's stop drawing. In fact, you can take that picture away. It's not relevant anymore. And the GPI stop draw command is there for your use in that setting. If you use stop draw in the setting of asynchronous drawing, it's very important that you resynchronize with the GPI synchronize command that we looked at under the presentation space functions earlier. There's a concept of dynamic segments, where dynamic segments are really those that are XORed. The purpose of XOR segmentation is to allow you to pick up a piece of a picture and to allow it to be dragged around. What you do then is you start the sequence by removing the dynamics from the picture by saying, okay, let's remove this set of segments from the picture. You change their attributes to dynamic, then remove the dynamics. And then you listen to, say, the mouse while the user is holding the button down. And every time a coordinate changes, you say, okay, redraw the dynamics. When you're all done with the picture, you can erase it. And in fact, if you know what a set of drawing orders, that is, what the binary representation of part of the picture store looks like, you can cause them to be processed through the process drawing orders command. Those are part of the functionality embodied in causing images to actually appear on devices. Drawing then and drawing control and the drawing mode are the constructs used to actually create images perceptible by humans from the representation in core of the segments and the attributes and so forth, which are part of the system. The next set of concepts, and I've already referred, hopefully I've referred to this already 2 or 3 times because this is a real tough one, is the concept of correlation. Correlation, as I've defined it, is what's called hit detection in the graphics industry. The idea is that you have a coordinate location. You know that the human is looking at a certain portion of a picture, and you want to find out what parts of that picture the human is actually paying attention to. You know that in your segment storage, in the presentation space, for the device which is being used, is a concept of a series of elements, and that those elements, clearly one of them is the one the user is expressing interest in. It's unusual for humans to express too much interest in the background of a picture, but might even be a selectable entity. In any case, what you want to do is to correlate the location that you know the human is looking at with the final resulting location on the screen, say, of any of the portions of your picture without having to run through all the transformations yourself. Correlation then involves you to detect what portions of the picture, what actual graphical elements have been selected by the human or are within the region that the human is paying attention to. The idea is that you draw the chain while keeping an open aperture, and every time an element, a graphical element, comes within that aperture, it's a coordinate space aperture, you want to be told, and that registers a hit, and the hit is stored for later inquiry. After the correlation operation, the data is returned to you one at a time. So you can figure out, for example, there may be 4 or 5 graphical elements that all lie underneath a particular coordinate location, and you want to get back information about all of them potentially. The correlation function is really quite simple. It's called Gpi correlate chain. What's not simple is the kind of control that it embodies. There's a tremendous number of parameters associated with this because essentially all of the control of the correlation is done right in real time, if you will, at the time the correlate chain call is issued. You tell us whether you want to correlate on any particular type of segments, that is visible and detectable only, or all segments, or the dynamic segments, or non-dynamic. You can either use the currently set aperture, which is in the presentation space, or you can scale that aperture instantaneously in the correlate chain call, or you can even override that aperture completely with data that you provide here as part of this call. What is returned is the number of actual hits that occurred. That is the number of times graphical elements at the bottom in a particular segment actually went through the aperture's image on the coordinate system. And that's what it returns to you, the number of those pairs and the number of hits which were detected in the correlation. Now, in order for you then to figure out, okay, was that the left tire? I mean, I know it's segment 2, and I know, in fact, that it's spoke 23 within the tire, okay, because it's element 18 in that graphical segment. What I now want to find out is how many segments, where was it called from? Because, for example, if it is segment 1 called very early in the use of the picture chain, then probably it's the left front tire. So there are additional functions which allow you to find out what the pick count was and to get back what the pick data is. Now, the pick data is a pile of segments. So if segment 1 called segment 12, that called segment 83, that has an element which is a polyline that actually caused the image of the pick to occur, then that's what you get back with these functions. I mentioned that you can set the pick window, and you do that, and you can find out what it is. Notice that this is not a rectangle, but rather a center and half extents to really emphasize that it's an aperture, which is what's being looked at here. These constructs are very complicated. They are in support of a fairly advanced functionality, and it is the only form of input that GPI does. GPI will correlate an input value with any of the final output coordinate values in the system as a result of running the chain. It turns out that you can ask for these data in either 2-byte or 4-byte formats. And finally, if the thing that was struck was a text string, you can find out which character in the text string was hit. In review, then, we've taken a look at the concepts and functions involved in the presentation space and DC storage of state and the use of devices. We've taken a look at the way in which segments describe a series of graphical calls of meaning to the graphical engine that's going to perform actual image creation. We've looked at the concepts of drawing, where drawing has to do with the actual creation of an image which is perceptible by a human from the binary data storage embodied in the presentation space. And finally, we took a fairly deep, I hope, but still for many of you, I'm sure, very inadequate overview of the concept of picking, which is the association of an input coordinate value with all of those locations in a picture which are nearby that value. These are essentially the concepts embodied in the functions that we have looked at to date. The next function group that we're going to take a look at is GPI's use of coordinates and coordinates, where coordinates are used to describe locations. During this portion of the talk, we'll begin to take a look at some video. I've got some images that are actual Windows application uses that will help elaborate some of the concepts that I want to talk about. But to begin with, the GPI uses a current position. Most of the graphical functions consume and remove a current position. That current position is therefore updated by many of the functions in the GPI. GPI's coordinate concepts are much richer than those of the GDI in that they embody the use of a number of coordinate spaces. The coordinate pipeline includes world coordinates, model coordinates, page coordinates, device, and finally media coordinates. The world to model coordinate system is really that. World coordinates are those which go into segments or perhaps directly onto the page if you're not storing a picture in segments. The world to model transformation then can involve either a segment as a whole or portions of segments, or may refer to called segments. These transformations are capable of performing scaling, shearing, rotation, and displacement or translation. In a little bit more detail, GPI supports the nature of world coordinates, which are still 16-bit integers in general, model coordinates, which are also the same 16-bit integers, but pushed through a transformation onto the page. The page may be set up by default, or you may use page coordinates themselves directly. And finally, the page coordinates are transformed into underlying device coordinates. Conversions from any and to any space are provided so that you can figure out where on screen, for example, a portion of your drawing will reside. The world coordinate to model coordinate system, then, as you can see on screen, involves a transformation of world coordinates into segments and from segments out of segments into the model coordinate system. World coordinates are those which are application convenient, and they either go directly into segments or they may go onto the page itself. Here we see an image of a tire described in a segment whose coordinate system underlying is 0 to 10,000 in each direction. This tire might make up part of a picture, say, and another part of the picture might be a car body, where the car body is here described in another world coordinate system of 0 to 2,000 and 0 to 500. All of these, then, are world coordinates. When we compose these images together into a system of model coordinates, what we'll find is that we can actually image a tire in a couple of locations on the screen. What we've done then is, as the output of reading the drawing chain and the constructs embodied in the transforms, what we've done is to position two tires, actually four tires presumably, right? But two of them are invisible because they're on the other side of the car. And you can see that what we've done is to move the tires from the coordinate system that they were defined in through a segment transform onto the 0 to 2000, 0 to 500 space in which the car is defined, car body is defined. Now you notice also that in the process of creating the car body, what we may decide to do is to rotate one of the tires. And in so doing, all we have to do is to update the transformation for that particular tire. As we move then from model space into page coordinate space, what we can do is to transform the numbers yet again. And in this case, what we've done is to take the coordinate system of the car body with the tires attached and to push it through the model transform so that the 0 to 2000, 0 to 500 space moves into 0 to 18,000 and 0 to 6,000, where these are page coordinates defined in hundredths of inch. Now in this case, the drawing is now suitable for drawing on an E-size plotter, for example. And essentially what we'd get is a full-sized car that's about 54 inches high and something on the order of 145, 50 inches long. These are the page coordinates. Page coordinates, for those familiar with the numbering in the graphical coordinate system of GDI, are the coordinate system used when you want to specify physical sizes, which are portions of inch, portions of pixel, or perhaps even portions of millimeter. The page coordinates are output from the segment plus the model transforms, and one can define a viewable window on the page which clips things. By the use of various transformations, you could make the entire car with its associated tires appear on screen, as we do in the video here, or you might otherwise want it to appear as a full-size engineering drawing. Page coordinates are then mapped into device coordinates, where device coordinates are relative to the client area origin. If you have use of a presentation style device, that means the whole addressable range of the device, because all the sharing of the device is done serially. But if you're on the display, it may be different than that. It may be the anchor of your Windows client area. The device coordinate system is at the intrinsic resolution of the device. So that if you have an image which is, for example, 4 inches by 3 inches, in a system which is on a display which has a resolution of 72 inches per dot horizontally, what you'll have is that the 4-inch horizontal maps to something on the order of 340 coordinate locations. It is the responsibility of the entire page to device coordinate mapping system to make sure that all the coordinates are transformed appropriately from the page coordinate system into the device coordinate system. Finally, at the very bottom of the coordinate pipeline are media coordinates. The media coordinates are relative to the true origin of the device. They are in device resolution, but they may not yet be the names of device locations because media coordinates are anchored at the lower left-hand corner of the device itself. There are a number of functions associated with creating and using the transforms associated with modeling and segmentation. In particular, you can set the segment's origin or find out what it is. You may set a transform for a segment, as it's called. This transform is, if you will, conceptually at the head of the set of instructions that make up a segment, graphical segment in the presentation space. And you may also set a model transform, which is the output of reading the drawing chain on its way onto the page. When you call a segment hierarchically, you may specify an additional transformation. Notice that in each of these transforms you have scale, shear, which is an angle from the original upright axis. You have a rotation, and finally a displacement. Type is a parameter that specifies whether you want this concatenated with the current transformation or to replace the current transformation, and whether you want it concatenated fore or aft. All of those concepts are well described in the typical textbook on graphics and graphics segmentation. When you want to actually view something, you can set up a window in modeling space and set it up to be uniform relative to the actual coordinate page locations as they're being used now. You can find out what that window is. When you want to set up a viewport on the page, you can set that viewport, find out what it is, and you can also set a default type of view. Notice that we begin now, the default view has to do with scaling, shearing, rotating, and displacing. But beyond this point, everything is going to be rectangular. When you want to set up the transform from the page onto the device, you can set up a window on the page, you can set up a viewport, which is on the device, if you will. Notice, for example, that the page window is contained within the presentation space, while the page viewport is actually on the device context itself. And you can find out what the current viewport size is. Again, something I've not referred to, but notice that each of these functions is defined by the top end of the transformation. That is, when you set a segment transform, it has to do with the segment going into model coordinates. When you set a model transform, it has to do with going from model into page coordinates. And when you set a device transform, it has to do with going from the page onto the device. Those are a quick review of the functions which are available to you to compose, to place into segments, to use as you call segments, and to use as you model a picture onto the page coordinate system. There are additional functions related to clipping and so forth that we'll look at a little bit later. But those functions all have to do with the transformation of coordinate values and the way they will ultimately appear on the attached device. The next set of concepts we want to take a look at is attribute concepts, where attributes affect the appearance of graphical primitives. Coordinates, again, affect location of those primitives. The attributes that are supported by the GPI include color, the size of an element, that is, should a line be wide or should it be narrow, the style of an element, that is, should it be an interrupted line or a dashed line or dotted line or what have you. And finally, some control is provided over the fidelity with which the image must be created. That has to do with the fact that you might say, well, okay, I've asked for color, but I don't really care about color. You can do something else if you like. Fidelity embodies the principle of graceful degradation. The last thing we want to have happen when you ask for a red line on a black and white device is for the system to hang and for the user to have to reboot. The principle of graceful degradation allows a device to do the very best job it can at mimicking the requested attributes. And there are a number of functions and stylistic conventions related to the way in which we will degrade your request for colored lines on a device which is black and white. Ultimately, though, that mapping and that degradation is a function of the device driver itself, and it's up to the device manufacturer, driver writer, to make those decisions. Further, if your application is such that you really want to know what are the exact capabilities of a device, you can find those out and therefore avoid any automatic degradation of the appearance of your image. You might, for example, want to adjust your use of attributes for geometrical and graphical elements depending on whether a device has color or not. While the GPI provides a great deal of insulation for you from those device characteristics, it is also true that the GPI provides you ways to find out exactly what a device is capable of doing so that you can exactly use the device and avoid any of the automatic degradation when you've requested characteristics that don't exist. Now, using this matrix, I want to begin to take a look at the ways in which you can set the attributes for various constructs that you're going to draw. On the left, the axis is one of color, size, or style, whereas along the top, horizontally, we've got the type of primitive, be they markers or lines or text. And there are a number of ways that you can set values for individual elements. That is to say, explicitly, attributes can be set in three different ways. First of all, attributes can be set individually. You might want, for example, to specify the size of markers. used to illuminate coordinate locations. You might want to set the style of lines to be interrupted or dashed or dotted. And finally, you might want to set the color in which text will be imaged individually. Functions exist for doing that. Additionally, you might want at once, in one fell swoop, to set all of the attributes for one of the types of elements. For example, in this case, lines, where you're going to set the color, the size, and the style of lines all at once. This is very much like the GDI's concept of pen. Those of you who are moving an application from Microsoft Windows for DOS and using the GDI call into the OS2 Windows Presentation Manager system will find that the use of the bundled attribute concepts embodied in the all attributes of one element primitives will be very helpful in migration. Finally, there are a couple of primitives involved with setting one attribute for all of the elements. You might want, for example, to change the color of everything to be red, and you can do that with the one attribute for all elements functionalities. In addition to the specifications above of what it is that you want a marker to look like, for example, or how you want text to look like, you can also either choose to replace these attributes so that you can recall them later, essentially push them on a stack, or you can overwrite the current attribute. In this case, what I've got is the current marker type is blue, color is blue, the current line style is dashed, and the current size of text is 12 points. In the next slide, what we can see is that what I've done is to push the color blue, so that's the old color of markers. The new color is now red. The style of lines has been changed rather than pushed, so that I can't recall it. This diagram is slightly in error. There should be no box behind the solid box, but the new style of lines is solid. And in the setting of text, I've made text 18 points, but I've pushed the O value for recall. There is, in fact, only a single stack from which values are recalled, that is, popped. And there are constructs that allow you to do that. There's another concept in the area of attributes which has to do with the way in which default attributes are acquired when you create a presentation space or associated device context with it. Default attributes are, in fact, settable, so that if you wish to restore, for example, all the attributes to some state which is not native to the way the presentation space actually woke up when you created it, you can do the begin defaults call and then make a bunch of attribute calls. Each of those attribute calls will reset the default attribute, and then you can end the setting of those defaults. Later on, when you restore the presentation space to its natural condition, what you'll get is the natural defaults the way you've set them. In order to get back to the original defaults, often referred to as the default defaults, you can get back to them with sentinel values used within the begin and end defaults bracket. Often that value is 0. Because you can push and inquire attributes and pop them off of the stack, you can set the mode to be push and set or set only. And if you have a stack of attributes, you can pop things off of them. In terms of setting attributes, you can set all of the attributes for one element using the dmask and the amask, as well as the attributes list. The dmask specifies which attributes are to be reset to the current default values, and the amask is used to specify which attributes are to be set to a value passed in the attributes array. You can figure out what the attributes are by inquiring them. The statement that the amask allows for short attributes is that if you only want the first couple of attributes off of something, you need not allocate a data structure, which is the entire size of the attributes for that particular construct. These attribute functions, then, are all related to the way in which you can control the appearance of the graphical elements as they will occur on a device. GPI has another very rich set of functionality related to the management of color. These color concepts effectively allow you to map logical colors from one presentation space or from one device context into another. Color indices are attached to physical colors by your definition of a color table, if you like. And when mapping from one PSDC combination to another PSDC combination, that mapping can be a logical mapping. The way in which we do that is to provide you with functions that allow you to create a logical color table and to find out what that color table is. Now clearly, any color table has got, any device which it performs color has got a default color table, if you will. But you may want to use that color table in a very careful fashion or even to reset it. GPI provides you with functions to control that mapping from one to another. And lots of different ways. You can set a range, you can set a few indices. In a sparse array, you can set one index at a time, and you can find out what the current logical color table in a PS is. When you want to actually use a color table on a device, GPI provides functions that allow you to realize that color table. In the video here, what you can see is an image on the left. What we've defined is the way in which you might actually want to specify that the color index 1 is to be associated with 110 units of red, 80 units of green, and 235 of blue. On a device which supported full 24 bits of color, it would be the case then that those colors would be realized directly from that color table. But on a device which has a much sparser color table in terms of the number of indices it can support, what might happen is the system would have to actually map your requested colors and the indices in, say, a raster primitive onto the available indices. In this case, what I've illustrated on the left is an unrealized color table which has the essentially 8 bits each of R, G, and B. And on the right, the effect of realizing that same color table on a device which supports only 1 bit of each of R, G, and B. In particular, what happens is the color index request for 1 is going to get mapped to solid blue instead of blue diluted with some red and some green. The color index for color 2 is going to be mapped to a solid red instead of having little bits of green and blue mixed in. And finally, the color index for 3, which is a request for green mixed with some red and blue, is going to get mapped to all green. On a device, then, after realization of the color table, we will perform any mapping of color index requests in bitmap primitives from the logical color table onto this available color table. Now, it may happen that if you realize a color table at the same time other applications are running, that you will change their mapping of the colors because they will have presentation spaces of their own and they will be using pixels in a conservative fashion. It is not recommended, therefore, that you try to manipulate the color table in a setting beyond your use of the entire display screen. But clearly, in the use of other devices, presentation devices in particular, it makes logical sense to use the color table constructs. When you're done with the use of a color table, you can find out what the color data is. You can find out all about how many colors a device supports. You can figure out what the real colors associated with various indices are. You can find out what the nearest color is going to be. In the case, for example, of our example that we looked at, the first index would turn out to be all blue instead of partially blue and partially red and green. You can find out what the nearest index is to a color that you want, and you can find out what the actual color is for a particular index. You can set the color which will be taken on by any foreground drawing, and you can set a background color as well. Additionally, you can define the mixture, the 2-operand Boolean operation that will be performed when you draw things like lines and curves. That we call mix. It used to be ROP2 in the Microsoft Windows GDI. It's now called mix. And you can also specify a mix for the background, where the mix available is not the full 16 Boolean operators on 2 sources, but rather only opaque and transparent, which are defined in much the same way as we have used them in the past. GPI then provides a rich set of color functions allowing you to control the way in which color attributes available at a device are actually used in your drawing of images. There's a rich set of functionality associated with your finding out what the color capabilities of the device are, and that allows you to control the way in which your images appear color-wise. Regions are a GPI construct used to support the clipping of your image to a set of device coordinates. Regions are very device class specific. If you create a region for a particular DC, it is important that you only use it in devices of that class. They are always in device coordinates as you specify them, not transformed at all. They embody sets of rectangles, and they're very useful for performing clipping. The functions available to you for use of regions involve the creation of a region, where you pass in a bunch of rectangles and an array of values, lower left, upper right, which will make up the region. If you decide that you want to reuse a region handle, but you don't like any of the data in it, you can reset all of that data with a set region call. If you forgot what's in a region, you can find out the bounds around, the tightest bounds, or you can enumerate all of the rectangles that make up a particular region, and you can find the tightest bounding box as well. There are a number of operations supported for combining regions one with another. In this slide, what I've attempted to capture is the way in which the destination is built out of the source region A and the source region B. In this case, note first of all that destination may be either the same as either of the sources. If that is the case, on return the destination will contain exactly the destination stuff, but the original contents of the source used as destination will have been changed. The mode is the operator which specifies whether or not you want the intersection, that is the Boolean AND of all the rectangles which are common to both regions, whether you want the OR, that is the set of rectangles which is in either of the two input regions, whether you want the XOR, the exclusive OR, which is the set of rectangles that are only in one and not in both. The final two modes are simply provided they are not Boolean operations, they are rather set operations. The differencing subtracts from region A all those rectangles which are part of region B and returns the result in the destination. And the copy simply creates a copy of the region A in the destination. You can guess that all of these functions are very valuable in the performance of the complex clipping associated with windowing. We provide them to you because they may be additionally useful to you in your use of the screen real estate. Functions are available for you to find out whether two regions are equal. You can move all the coordinate locations in a region by offsetting them. You can inquire whether a point is within a region and get a yes/no result. You can inquire whether a rectangle is within a region and get a result that depends on the parameter that you specify as being outside or partly in or totally in. That is the region that you query. When you're done with a region, you can destroy it. You can also use a region to paint an area, that is, fill an area with a pattern or a bitmap. Uses the current pattern attributes, and it actually does drawing directly on the device. You can use regions to select at the device coordinate level a new clip area. You can find out what the tightest clipping box is. You can move the clipping region. Once you've made a region into the clip region, any operations you perform on the clip region affect that region later on. You can intersect a clip rectangle so that the only area you get to draw on is the intersection of the clip region with the boundaries that you specify. You can exclude a clip rectangle from a region so that you can save, for example, all the bits in a particular area if you've gone to a lot of bother to create them and don't want them altered. Clipping functions are provided to support your use of viewing on the device, and the set viewing limits and query viewing limits have to do with a rectangle on the page. The begin clip area and the end clip area are your way of specifying a complex clip shape which may be made up of numerous line segments and parts of arc and, if you will, polygons which may have complex borders. We will look at them again later when we talk about the line functions, but suffice it to say at this point that you can clip to arbitrarily complicated shapes using the clip area function. You can set viewing again at the level of page coordinates with the clipping functions having to do with pages in the graphics field. We've now discussed those GPI functions related to geometry, related to the control of attributes, that is, the appearance of things as they occur on the device. We've taken a look at the incredibly rich functionality which GPI provides for your control and use of color on devices. And finally, we've taken a brief look at the ways in which you can additionally control the way in which images and pictures are clipped on the device as they are realized. To this point, we've taken a look at the way in which GPI provides functions that control the coordinate locations and the appearance, building of pictures, storage of pictures, and so forth. And we are now finally ready to turn to the elements, the functions that GPI provides for actually creating images which will be perceptible by humans. The first group of such functions is the marker group. Markers have as their purpose the illumination of coordinate locations, simply by putting some symbol at each of a set of locations. In order for us to know what symbol you want used, you can select a marker set, about which I'll say more when we talk about text and character sets and symbol sets. But suffice it to say that a marker set specifies which logical character set the index, the current marker image will be taken. And from that set, you select an index, which is going to be the current marker. The system provides a number of markers by default, all of which are things like closed box, open box, asterisks are, and so forth. The attribute functions continue by allowing you to specify a size for the marker in world coordinates and a mode, where the mode tells the system how carefully you want it to image the marker. It may be, for example, that a marker is very large, and even while the center of a marker is off of the currently usable drawing area, one portion of an arm of an asterisk might in fact be within that current drawing area. And the marker mode specifies to the system whether you want to see any such pictures or whether a marker can be clipped solely because the center point is invisible, that kind of thing. Once you've set up the attributes for a marker, you can actually create one of them or a bunch of them by passing in a single coordinate location or an array of coordinate locations. GPI's line functions group is used to actually draw borders around lines or boxes, or to draw curves. You can create complex areas by combining curves and boxes and lines into stroke sets, and area borders are also drawn with the line attributes. GPI supports a few predefined types of lines. These are solid and dashed and dotted and so forth, as well as loadable line types. In the video, what we've illustrated is the number of types of line that you can draw. Just a couple are shown here, as well as wide lines and so forth. The user settable, the loadable line types, are new in the GPI, and up to 192 of them may be user defined. The user definitions are always interpreted in device coordinates, and therefore in a device which has a non-square pixel aspect ratio, you may find that the appearance of a user-defined line differs in horizontal runs and vertical runs. Line attribute functions are provided to allow you to set the width of a line, or to set that width can be either nominal width or a scaling of nominal width. And you can also specify whether you want to use exact world coordinates. In order to allow you to control the appearance of line ends, we have added a line end type function. You can specify that you want line ends to be flat or square or round. This has to do with any time you do a graphical element that has two line ends, the ends of those lines are actually drawn with the current line end type. In order to give you some control over the appearance of joins between lines which have multiple points in them, we provide the bevel, the rounded, and the mitering type of line join. These are useful in the setting of lines which have more than one point that make them up. And finally, when a line embodies a large number of pixels on screen or pixels on a raster type device, you may want to image that line as actually a pattern. We provide a pattern symbol set and a pattern symbol for you to do that. This allows you to use, for example, hatched appearance for borders of lines. This is new in the GPI over the Microsoft Windows GDI. The predefined patterns for lines include intensities and hatches. Once you set up all the attributes that you want to use to image lines, you can actually begin to perform some line functions. I've included the current position functions here for completeness sake because they really don't fit anywhere else, and they embody not so much an imaging capacity as the movement of the coordinate current location. You can set the current position and you can find out what it is. In the event that the current attribute is push type, the current position setting function will have the effect of pushing that current position so you can get back to it later on. GPI's move function is provided in the event that you don't want to push and yet the attribute type is push. It overrides that current attribute setting. When you want to actually draw lines, then you can draw one line at a time, or you can draw through a bunch of coordinate locations. Both the GPI line and GPI polyline functions consume the current position. They therefore both have two ends, and polylines have n-1 joins as well. If you want to anneal a number of line calls together, say, for example, you have self-intersecting borders or boundaries, or you want to draw a very complicated line, and the strokes primitive allows you to bracket a bunch of line calls. What it does is to enable you to turn a bunch of what would otherwise be line ends into a set of line joins, and therefore anneal your entire figure together. In the video, what we're showing here is the fact that this allows you to build complex figures. The figure on the left is fairly simple, but cannot be described without a functionality like the begin and end strokes functionality because it has a curved bubble at the left. The other strokes primitive illustrated on the right in the video is one which is self-intersecting. Now that doesn't mean much if what you're doing is painting every time you draw the line around. But what if you're using, say, a complex Boolean operator and a pattern as you draw the line? What may happen, for example, in the setting of XOR, is that the final appearance of a pixel on the screen is going to depend on how many times you've drawn across that line. In these cases, we've shown no particular point being drawn more than twice with this series of calls that resulted in the shape on the right. But you can see that arbitrarily, individual pixels may have been drawn arbitrarily many times. By beginning of strokes, doing all of the line calls, the arc calls, the curve calls, and so forth, and then ending of strokes, you enable us to ensure that each pixel is painted only once with the line mix, or the current foreground mix operator. And that allows you to perform beautiful Boolean operations on those constructs. The begin and end strokes functionality, then, is very important to the elaboration of complicated shapes. Line functions, many of them now are curves. We support the notion of a three-point arc. Here in the video, what you can see is that the three-point arc begins and ends at the locations which are part of the parameterization, and the curvature is actually specified by the middle point, the x2, y2 point. It is not required that the x2, y2 point be at the center of the curve, which is a three-point arc. And the purpose of three-point arcs is to give you absolute control over the exact coordinate location at which that arc begins and ends. This is very useful, for example, in the setting of the strokes primitive, where you want to run a polyline up to the beginning of a curve, do a curve, and then run another polyline from that point. The other construct which can allow you to draw curves is called partial arc. Partial arc does not give you the same kind of control as you have in the three-point arc. Partial arc, on the other hand, does give you a pi wedge control, and it scales. Notice here in the video what we've illustrated is the fact that as you scale the primitive, as you change the aspect ratio of the primitive, say making it flatter or perhaps making it taller, that the actual angle at which the pi wedge is drawn changes. This is because of the use of the m, which is a scaling 32-bit value from the currently specified arc parameter function, and the TS and TE are in radians rather than in degrees. What this allows is us to take a pi wedge and turn it into an ellipse wedge and have the area subtended between TS and TE to remain the same. The partial arc function is therefore very, very useful for actually drawing pi wedges and so forth. Because you don't have exact control over the beginning and ending coordinate location of the edge of that partial arc, it is not as good for building up a complex border as in the line strokes primitive would require. These then are lots of ways in which you can draw lines. There are two more, but I saved them for a little bit later. The next group of functions we want to take a look at are the solid functions embodied in the GPI. Each of these functions takes a control parameter, and as you'll see in the video, that control can specify whether or not you want the interior only, as in the rounded rectangle, or whether you want the border only, as in the pi wedge, which is a bunch of pi wedges all put together, or whether you want both the interior and the border to be drawn. The shapes, primitives that we provide, therefore, are effectively our polygon and structured geometrical area primitives. In order to control the way in which the interior is imaged, we need to allow you to specify a pattern set. In addition to using any of the predefined patterns for areas which include solids and hatches as well as intensities, we also allow you to use a bitmap of your own choice as the pattern to be used in the interior of areas and solid functions. The GPI solid functions begin with a box primitive, where the box primitive, as illustrated on the slide, includes control over whether or not the corners of the box are actually going to be rounded. What you do is you provide, first of all, a control specifying whether or not you want rounding to be performed, and the additional parameters, HR and VR. These are the horizontal and the vertical rounding parameters, where those specify in world coordinates the partial ellipse that is to be, or the full ellipse that is to be used to round those corners. In the event that HR and VR are both 0, then you get no rounding at all. In the event that HR and VR are in fact the width and the height of the rectangle, what you get is a full ellipse. What we have found in practice is that values of between 1/5 and 1/3 of the horizontal and vertical size of the rectangle create pleasingly rounded borders on a box. All of those then, what used to be the rectangle and the round rectangle primitive, are crunched into the single GPI box function. The ability to define wedges and ellipses is captured in the full arc primitive and the pi slice primitive. The full arc is centered at the current position. The border may be controlled as on or off, as well as the interior being on or off. And the M allows a scaling from the current arc parameters as the arc is created. Pi slice is just the same, but is closed to the current position and takes the TS and TE parameters, which are in radians again and not in degrees as they were in the previous partial arc primitive. The two solid functions that may not in fact be solids but have to do with complex, or three actually, functions. Two of them are shown on this slide. They are the polyfillet. Polyfillet is a series of conics which are guaranteed to pass through a number of the points in the array passed. Every other point in the array passed is a bounding on the conic section to be used. The difference between the polyfillet and the polyfillet sharp is that the polyfillet is the shape of the polyfillet, whether it's, for example, to be circular sections or ellipsoidal or parabolic sections, is in fact device and implementation dependent and not controllable by you. Polyfillet sharp says, I really care whether ellipses or parts of circles are used for each of the portions to be filled. And using the S parameter, you can set whether the shapes between sections are to be portions of circle, portions of parabola, or portions of ellipse. The polyfillets are not guaranteed to be smooth at the intersections of the piecewise conics. They are, however, very useful in the event that discontinuities in the higher order values of slope are allowed or not visually unappealing to you. In the event that you want complete control over the higher order, in particular the second order derivative of your curves, we provide in the GPI a polyspline. This is a true lofted Bezier spline, and the point list includes all of the control points that you need. The guarantee here is that these piecewise conics will be continuous in both the first and the second derivatives. In the event that the polyspline is closed by having been placed, for example, into a shapes primitive, you will get the kind of closure and, for example, line end and line join styles as specified in the line attribute set. Finally, if you actually want to draw one of these things and have it become a filled area, you can do a begin area and end area. Control, again, specifies whether you want border or no border to be drawn as part of the area. This is really our polygon primitive. But notice that because it's an area, you can, in fact, take a portion of your polygon and make its borders non-linear. That is, you can use the curves as part of your border for a polygon now. Additionally, we provide you control over whether alternate filling or winding filling will be done. Alternate is illustrated on the slide on the left and effectively is a raster scan method for filling the interior of a complex shape. The winding mode is, if you will, the geometrical higher order kind of filling style, and GPI provides you control over whether your areas are filled in winding or alternate fashion. We've taken a look now at the geometric elements GPI provides, those which relate to the illumination of coordinate positions, those which relate to the connection of coordinate locations with straight lines and with curves, and we've taken a look at some of the ways in which you can define solid shapes. One of the unique aspects of the GPI is its ability to allow you to pour a bunch of curves and lines into either a strokes primitive, which will be a bordered primitive only, or into an area primitive, which will be a true polygon. These make up the ways in which GPI allows you to create vector or geometric style primitives. We've looked at the functionality in GPI that is involved with coordination of coordinate systems, of attributes, and then we took a look at the constructs and the functions related to the creation of geometrical type graphical elements. What we're now going to turn to is the two areas of functionality that are really unique in the GPI as inherited from the GDI and in fact somewhat enhanced. These functions have to do with Raster concepts and the text concepts as they're embodied in GPI. Beginning then with the notion of rasters. First off, very early on I spoke of rasters as being an array of samples, that is an array of intensities or colors at locations. To us, that's what a raster image actually is. The raster functionality in the GPI embodies functions which are capable of performing scaling and translation from one part of a device to another part of the same device, or from one device onto another of raster elements. In addition to scaling and translation, which were pioneered in the Microsoft GDI instruction set, We provide color conversions. As you move from one device to another, color conversion may become of value. Microsoft's GDI did bi-level conversion, that is from foreground pixels onto foreground color and from background pixels onto a background color as you move from bi-level maps, sometimes called monochrome maps, but monochrome terminology is not accurate. Monochrome can come in a number of intensities, meaning monochrome is not the same as 1 bit per image pixel. But in any case, so these are the images I call bi-level. And Microsoft's GDI pioneered the use of transformations from bi-level images into color images. What is new in the GPI is a much richer notion of the transformation of color images to color images, where one may have an image made up of 3 bits per pixel on one device and want to put it onto a device which is capable of rendering up to 8 bits per pixel. The color-on-color mapping then involves both spatial resampling, scaling, if you will, of the input image onto the output device, and resampling in depth, where a color at index number 1 in device 1 might be mapped to an index 2 in device 2. On the video, what we've got is an image of the realization of the color table defined in the middle as unrealized onto both a device A and onto a device B. What happens is that the input images, which are defined in full 8 bits of each R, G, and B in the input bitmap, are translated to resultant color indices on device A and to another set of resultant color indices on device B. That is, if you were to move from a presentation space in which the images were stored with a color table that was a full 8 bits each of R, G, and B onto device A, what you discover is that all of the pixels defined as index 1, that is 110, 80, 235, in the input image were mapped to color index 1 on device A and mapped to color index 2 on device B. This is to illustrate the richness with which the logical color tables, when realized for particular devices, can support conversion of color to color. Additional concepts of the raster image, of the raster functionalities are, first of all, that we now have, in addition to the bit block transfer functions, commonly called bitblit, which are bitmap operators, we have an additional function which is called image. Image supports only bi-level data, that is, pixels which are on or off, that is, 1 bit deep at each location. Image data is placed at current location, and the function call image includes the data. It's what you might call an immediate data kind of primitive. That is, the data are not indirect, but rather embodied within the function call itself. Images and image calls may be stored in segments for later redrawing on screen. That means that they can be sheared, translated, rotated, and so forth as they are actually placed onto a target device. The bitmap operations are those operations which move an area from one place to another. They involve the support of both bi-level and color images on input, and functions are provided which move the data, which is not defined within the function, but rather referred to by values within the function. The functions may include implicit conversions of that data from one color depth form to another color depth form. That's a whole lot to say in one set of mouthfuls having to do with images and the bitmap operations, but let's take another look then at what I'm talking about. The Gpi image function includes with it a notion of the way in which the data are specified, the height and the width of the actual bitmap which is included, the amount of that image stored in the length, and then a buffer which is associated with that data. No coordinate conversion is implied in the image function itself, albeit the data may be transformed as they come out of a segment, for example, if they went into a segment, through the model transform onto the device. There may be some form of transformations applied. The data are defined in the image buffer from left to right and from top to bottom. And the upper left-hand corner of the image is placed at the current location at the time the GPI image call is made. This is what I call the immediate data function for bitmap operations and supports only bilevel data, that is, data which has pixels that are on or off. At the time the image is actually drawn, all the on pixels take the foreground color and all the off pixels take the background color, whatever that color might be on a color device. That is the only form of primitive which can be stored and includes the data in segments. The other raster functions are related to the movement of data from one portion of a screen to another. And what we'll take a look at in the video is the way in which you can actually create these images. But to begin with a little verbal discussion, the GPI bitblit operation takes a destination presentation space and a source presentation space. It is a non-destructive block move, so that if you move an area onto itself but backwards, we'll make sure that you don't destroy the data as you do that. Or if you move an area from one place to another where it partially overlaps, we'll make sure that the source data is not destroyed before the move. Our bitblit operator captures within it, first of all, the number of points which are passed in the coordinate array, and the decision as to whether or not you want stretching to be performed or no stretching performed is going to be dependent on the number of data points you pass in. In the event you specify 3 points only, you lower left, upper right, and a new lower left, the bitblit operation will simply move all of the image data, that is, pardon me, all of the picture in the rectangle defined by the boundaries specified by points 1 and 2 to a new origin at the point specified by location 3. In the event that n is 4, what we will do potentially is to actually stretch the image as we operate on it. And we'll talk a little bit about the way in which the ROP raster operation and the mode parameters are used to define the way in which bits in the origin, the source, are blended with the pattern and finally placed onto the destination during the bitblit operation. What you can see on video here is that we've got a set of bits that we've placed on the screen, one ellipse and 2 rectangles with different fills and borders. And the first thing we're going to do is to use the cursor to place some points around the image. This is the old GDI. Notice I'm defining upper left and lower right. And now we'll define a new origin and simply punch the blit button. What we have done then is no spatial resampling at all in this move. Now we can again pick up the same set of bits, upper left, lower right, and we'll place them into a tall, skinnier rectangle and do a stretch blit into that area. What we've done, as you can see, is to resample in space, throwing away some columns of information and duplicating some columns of information to give you an image which is stretched into the new location. Again, we could stretch and change the aspect ratio to be a long but not very tall rectangle and punch the stretch blit button and see that this resampling can involve either stretching horizontally or stretching vertically, and that's what the stretch blit operator is. Our bitblit function for GPI captures that same functionality in the decision that you make as to whether to call bitblit with 3 or with 4 coordinates. The other operators in the bitblit function specify, first of all, whether or not color mixing is to operate and how it is to operate on the input portions of the bitblit operation. Bitblit is actually a 3-operand function. It takes pixel images from the source, from the destination, and from the pattern, and it merges those into a new color value or bit value, pixel value at the destination. 256 Boolean operations are defined as part of the ROP, which is passed in as part of the bitblit. These Boolean operations allow all possible combinations of opacity and transparency for 1 bit per pixel image, pattern, and destination. For purposes of color, however, they are less than complete, having to do with the specification as to what's going to be imaged on the screen. The result of that fact, that the ROP does not fully specify how to merge color bits from the source, destination, and pattern when you have to do spatial resampling, is that we have also included a mode parameter. As you can see on the left, if the operation is bitlit because you passed in only 3 coordinate locations, the input image on the bottom is exactly transposed onto the device as output. There is no sampling performed. If aspect ratio on the target device is not square, you will get a non-square resulting image on that device, but there is no need for us to combine values. In the event, on the other hand, that we have to combine rows or columns in the process of moving from the input source, pattern, or destination set of values onto the destination set of values, we will need to perform some kind of operation, and we provide you with additional values of the mode parameter that allow you to specify whether or not we should simply take all the Boolean bits in the number of pixels that are going to be merged into a single pixel. So in the second column here underneath the word OR, what I've tried to illustrate is that each input group of 4 pixels, as defined in the bottom drawing, is going to create a resultant image pixel in the upper, the result of the operation. In the setting of OR, what we want to specify is that if any bits are on in the source pixels, the pattern pixels, or the destination pixels in the area from which you are taking things, then the result is going to be on in the result. If all of the bits are off, then the OR is going to be null, and the result bit will be off. The next column over is the AND column, and here what you can see is that the only pixels which are going to be on in the result are those pixels, all of whose source pixels had their bits on. And finally, you can see that since Boolean operations on color indices are not real keen to the human eye necessarily, what you may want to specify is that we should just drop the columns and the pixel and the rows of pixels that we're not using. And in this case, what we've got is 4 individual pixels whose values are simply transferred from the input at the bottom to the output 2x2 matrix at the top. And that is the drop operator, which is the mode specification for bitlit. None of this is trivial. None of it is going to seem immediately apparent at first pass. What these operators allow you to do, however, is to control the way in which your bitblit operation is performed from one device onto another, or from one area of color depth into another, together with the color conversion, the logical color table as realized in a device, the stretching, and the transforming of color table values. We give you much more power than any other system, period, bar none. One of the reasons that it's going to be fun to study this functionality is that it doesn't exist anywhere else except in the GPI. Additional raster functions exist in the GPI to allow you to set a particular location to a current color, to find out what the color is, and we even support flood fill. Flood fill is bounded by a color that you define, and it is also bounded by the currently valid drawing area on a particular device. It is implementation dependent whether color flood fill works on a presentation style device like a printer that may do banding in the creation of its image and so forth. And finally, the next set of raster functions I want to look at allow you to load up a bitmap. When you create a bitmap, as seen in the bottom of this image, you can specify whether or not all of the red bits or the green bits or the blue bits for a particular pixel are together on separate planes, or you can specify, which is what we call the planar representation, or you can specify that perhaps the image has all of the bits for each pixel, red, green, and blue, packed together. The create bitmap function is sufficiently rich in its parameters to allow you to describe many, many possible input bitmap styles. Once you've created a bitmap, you may have stored some data of that type conformant with that data bitmap description on file, and you can get that from the file by using the load bitmap function. When you're through with the bitmap, you can delete it. If you want to operate on a bitmap, you can select it into a device context and get a handle to it. You can also specify its physical size if you want to try to have some control over how it should be stretched and ultimately actually imaged on a device. every device which is a raster device is going to be capable of supporting the conversion of some bitmap formats into other bitmap formats. You need to be able to find out what they are. There are two kinds of descriptor for that purpose. One is the bitmap formats. You can find the count of them with the device query capabilities function, and that will tell you what kinds of bitmap shapes are blittable by this particular device driver. The other format conversion set that may be of interest is the number of outside formats that you can use when you pour bits or retrieve bits from a currently selected bitmap into another presentation space. Again, these functions are very rich. What we're going to do is to standardize a number of canonical, if you will, bitmap formats. Not just 1 bit per pixel, but 3 bits per pixel, 8 bits per pixel, and probably a 24 bits per pixel image will all be standard. And we will request and require in many cases that device drivers which register themselves as raster capable be able to convert from many of the kinds of representation, either planar or packed pixel, for various forms of bitmap from and to any of those data types. Once you've gone to a lot of effort to actually create a bitmap image or a set of pixels on some device, you may want to save them away for later on. And if you've got some bits that you've saved away, you may want to pour them back onto a bitmap for reuse. That is involved with motion and movement from the display onto a memory bitmap, and from a memory bitmap onto a current bitmap, for example, on the screen. The length and the buffer, as well as the offset parameter, allow you to do partial reads and writes of a bitmap. And that means that, for example, you may be getting the bits from a bitmap area that's 96K, and you can retrieve 5K at a time and be sure that you get the whole thing. The logical color table is, in fact, going to be included as part of this bitmap data. It is very unwise, and we're not going to help you figure out what the content of the data are, but you can certainly find out with other calls what the shape of the bitmap data is, how deep it is, how many bits per pixel, and how they're packed, and that will help you understand some of the conversions that will be required. In summary, then, the GPI bit, blit, and image functionalities are sufficiently rich to allow you to control the way in which image and color data, which is point sample intensity data, is going to appear on your target device, and allow you also to move data off screen for later reuse, and potentially allow you even to file data away for reuse on the same screen type later on. None of the operators involving color conversion or stretching of a bitmap is cheap in terms of CPU time, but we allow you sufficient control so that you can specify whether or not you want that work to be performed. The next area of functionality we're going to take a look at are the text area functionality. Microsoft Windows GDI pioneered enough information about text that you could begin to do typographical style work with the microcomputer. GPI continues in that vein by adding additional functionality for the use of text. Images, that is character glyphs, if you will, the appearance metaphor that's going to be attached to some index in a character set, may be either provided by the application, in which case we call them symbol sets, and the application simply says, here's the data. Later on I'm going to use this to draw text strings, or may be requested from the system, in which case we call them fonts. GPI's text concepts embodied in symbol sets is that applications install symbol sets into a presentation space for later reuse, and the symbol set includes the character image information. That image information may be bitmaps, or it may be strokes primitives, in which case they're just simply sequences of line and character and line and curve calls, each of which defines a character image for later use on a particular device. And finally, symbol sets really, in terms of number of attributes, have just a box size. That box size may be changed at will. Many of the other attributes are not relevant to a symbol set.